Hello friends, let's have a look at the legendary question. And today I prepared a question with the complex number and a very famous result that we often saw, but be able to prove it using the method that we learned from the complex number. What does that mean? Let's get to it. Okay, so yeah, the title of the video is "The Manners Make Man," right? So it's one of the favorite, the popular scene from the Kingsman, right? So, and want to associate with this from a tale that I don't know if it's credible, but the formula, the equation that we're about to unfold, the question that we're about to tackle, is often known as the common knowledge at Cambridge in the late 60s. So let's see what was the common knowledge, what was the manner they had in the time that made the man, right? So let's see the common knowledge of the 1960s, okay? So let's get to it. So before we do, you always know, so I'm not throwing some random question that are often advanced or difficult, but trying to connect with the problem that has already appeared. So I'm going to see problem question number 14, the question from the November 2014, which was the following DMT problem. So this is to work with the complex number, right? So here, yes, what we had to show was a DMT of the following kind, the 1 plus I tangent to the power of n and 1 minus I tangent to the power of n, where n was a positive integer, I believe. But here's the thing, that the problem of this problem here was that for the DMT, we know that we got to have the cis form, isn't it? So then we need to have a cis theta to the power of n, right? Then we know that it's cis and theta. And unfortunately, I don't have the cis here. I have only the tangent. So what is your deductive reasoning here is that I must make it into the form of somewhat in terms of sine and cosine so that I can associate. I cannot use the DMT right away. But here's the thing. So sure, if I quickly show you 1 plus I tangent is, if I then want to induce some form of a sine and cosine, I can do the rise over run, the sine over cosine. So it's going to be 1 plus I sine theta over cosine theta. That is great. Then I'm going to put into the common denominator. If I did, it's going to be cosine theta plus I sine theta over cosine theta. So that is great. And on top of that, what I'm going to do is to put into the power of n, you see? So that is great. Then I'm very happy to use the DMT, right? Because in the numerator, I do have a cis form, so that's great. So it's going to be cis and theta. I can use that. But unfortunately, I can't use it on the denominator because this is a cosine, so it's just going to be cosine to the power of n, right? So that is great. And then, yes, you know that it's just a conjugate, right? So every time you see the complex plus a conjugate, that's just twice of the real part of the complex number, isn't it? So that I have to tackle the twice of the real part of that, where the real part will be just replacing the cis with cosine and theta, right? Hence, I can derive it. So you already saw in November 2014 that if I got something of a tangent, not the typical trig ratio such as a sine and cosine, I can still use the DMT by using the sine over cosine, etc., etc. So that has been seen. So I'm just pointing out some questions that we have seen before. So this is November 2014. Let's move to the next year. So in May 2015, what we saw was to use the the expansion of a complex number in the two different parts, using the DMT, using the binomial expansion. So if I use the DMT of that part, at first I have cosine 5 theta plus I sine 5 theta, isn't it? And in the first part here of the problem, they have asked me to put into the binomial expansion. So why not? Let's do that. So if I use the binomial expansion for that, it's going to be sigma k is equal to 0 to 5, choose k, and then cosine theta to the power of 5 minus k times I to the power of k sine k theta. Right? So that's what I have. So k is the index of a sigma. So that's lovely. And from here, what I recognize on the problem here says that they want to somewhat find the multiple of 5, angular formula of the multiple of 5. Okay, that's interesting. Well, now you already know from the complex number, using the deductive thinking, if you want to associate with the sign, that's the imaginary part, isn't it? So for me, I want to associate with the imaginary part of that. So no matter of the method of expansion, either binomial or DMT, the imaginary part must be the same. So for this binomial expansion, you may expand everything there, having the 6 many terms, but I don't want to because I know already that I have to attack with the imaginary part. So for that one, I'm going to work with the k being 1, 3, 5, the odd terms, because that would then induce only the imaginary part. I want you to realize if the k is even, then it's I squared, 4, 6. It's just alternating plus minus 1, right? So that's the real part, and we don't want to have it. I want to just compare with the sign. So that is lovely. That is great. So then I'm going to associate with just k being odd. So if I let the k being odd, starting with 1, that's going to be 5 choose 1 cosine 4 I1 sine theta. And if I let 3, it's going to be minus 5 choose 3 cosine square. Why have I chosen minus? Because I'm going to let I3, but that's just negative I, isn't it? So I'm going to put negative I there, and then sine cubic. And then you can do the 5 choose 5 as well, letting the k to be 5. But I want you to recognize that that's exactly what we had to show, right? So of this problem, the essence of this problem, it actually unfolds a bit deeper, but you definitely want to check this problem. But in the May 2015, what they were saying here is, okay, I can use the DMT and then the binomial expansion, compare the real part, the imaginary part. So I want you to think about two things. From the November 2014, they were talking about putting the power n of a tangent, right? Of not the sine or cosine, but no problem. I can do the sine of a cosine and somewhat try to use the DMT. That's number one. Number two, I'm going to compare the binomial expansion with the DMT, okay? Then let's get to the legendary problem. So I want you to have a look at this legendary problem. So now what I want to do is to simplify this. I want to simplify this, but this is actually exactly the same. This is exactly the same. We were working with the tangent, right? But now I'm working with the cotangent, but not a problem, right? Not a problem, because for the cotangent theta plus I can actually make it as a cosine over sine. No problem. So I'm going to let this to be cosine theta over sine theta plus I. And then I'll let this to be what? The common denominator of cosine theta plus I sine theta over sine theta. Oh la la. Then I'm going to put into the power of n, isn't it? Sorry, I'm going to put into the 2n plus 1. No problem. I can still use the DMT as long as it's an integer, right? Then, yeah, on the numerator, that's going to be pretty simple. It's going to be just cis, what is it? 2n plus 1 theta. It is what it is on the numerator, right? It's exactly the same from the November 2014, isn't it? But now I'm talking about the sum of complex number, sorry, the difference of complex and conjugate. And I want you to already know that this is going to be twice of the imaginary part, isn't it? Of the complex number. So as you can see, so 2i, my bad. So that's why they put the extra 2i to get rid of it. So then you're going to just get the imaginary part. So I want you to realize it's no biggie. I want you to pause the video. I want you to try yourself, but this is exactly the same as the 2014 November question, but just slightly different from the use of the, the cotangent. But no problem. That's just the reciprocal tangent. That's just cosine over sine, and we can do the same thing. Okay, that's very good. So let's suppose we got that identity. That is a great. Now what I want to do is, okay, I've expanded using the DMT. And then you know the essence of a complex number is also to work with the binomial expansion and then try to compare, right? So what I would then suggest to do is to work this as a binomial expansion. I want to encourage you to expand this binomially. So let's have a look. So I'm going to do one by one. So okay, so instead of expanding by the De Morgan's theorem, let's try to expand by the binomial expansion. So now this is gonna be, I'm gonna let the substitution because I don't wanna meddle too much with the cotangent. So I'm gonna let t to be what? Cotangent theta. So that is great. So I have a t plus I to the power of 2n plus 1. Then I'm just using the method that we already know, right? So we a plus b to the power of k, as you know, it's just sigma k is equal to 0. Sorry, n 0 to n choose k. A to the power of n minus k, b to the power of k. That's exactly what I'm doing here, all right? So then I have, for that one, for this one, I want the sigma k is equal to 0 to 2n plus 1, 2n plus 1 choose k, t to the power of 2n plus k, so plus 1 minus k. Oh, I think I've done it wrong here, so sorry about that. So I think that should be 10 plus 1 minus k. So this should be here. Let me rewrite the 2n plus 1 minus k. That's what I want to do. I think that's better. I to the power of k. That's exactly the formula that I've used. So similarly speaking, I've written it well here. That's the correct one. But I want you to realize that's pretty much the same, except that this is the negative part, so it's going to induce the alternating term, right? So some terms are going to be the same. Some terms are going to be actually alternating. Understood? And so, yeah, if k is even, right? So I'm going to be particularly paying attention to this. But have a look. I wanted to have the difference. Right? So then I convert into the use of the binomial expansion. Now I want to see their difference and see what I get. Okay? Let's get to it. So what they have asked me to do is to find the difference. No problem. Now with the same sigma, I'm just going to put it to sigma inside. And then I try to factorize by the common factor of who? Sure, I got the common factor of 2n plus 1 choose k. That's the binomial coefficient, right? And then, yeah, sorry, I think it's meant to be t to the power of 2n plus 1 minus k, right? So sorry. So yeah, that I factorized, right? And I factorized I to the power of k as well. Then it's going to be just 1 minus negative 1 to the power of k, right? Negative 1 to the power of k. So as you can see, this is going to be, so that term alone is going to be either either 2 or 0, depending on the k, right? If k is even, my friend, you're right. Negative 1 to the power of k, for k being even, is always going to be positive 1. So 1 minus 1 would induce a 0. Whereas if k is odd, then it's going to be negative 1 to the power of odd. It's always negative 1. 1 minus negative 1 makes it double. So that's going to be always 2. And what's the typical definition that we give for the odd number? So sure, I'm going to let 2m plus 1, where m is an integer. Okay, so that's the definition of what is it? Odd number. That's what I would do. Okay, I'm going to let k to be 2n plus 1, and then I'm going to plug it in. And sure, I skipped some parts, okay? So this is a homework. I want you to be able to convert this series, okay, realizing that I don't care about the even terms because they will be canceled out if you subtract. Okay, so I'm only interested in the odd number. So as you can see, if I start plugging m to be 0, if I put 0, that's 2n plus 1 choose 1. If I put 1, that's going to be 2n plus 1 choose 3. You see? So those are the great expansion, binomial expansion in a simplified form. If I let k to be 2n plus 1, you need to be able to work with the algebra of the index of a sigma. So I would leave it as an exercise. Please work on it and see if you can do that. Okay, so I want you to realize what I'm trying to do. I had an expression in the complex number to the power of 2n plus 1. But I used the DMT to simplify in the trig value. I used the binomial expansion to induce some sort of a polynomial here. Okay, that's great. So I just put starting from m to 0 to n, I got these values, right? So that's great. So this is a polynomial. This is a polynomial. Okay. So far, we use the DMT and we use the binomial expansion to induce these, right? Using this substitution here. Okay, that's interesting. Well, what's the time now? It's now time to equate them because no matter what the method of expansion, we started with the same thing. So here's going to be the bridge, isn't it? So that I can equate them. So I'm going to equate them as the following. So that, my friend, is the imaginary part, and that is the one with the binomial expansion. And that's great. But hold on a sec. You're working with the polynomial, all right? You're working with the polynomial. And what we are more familiar with is maybe working with the x. So right now, I'm going to let t squared to be x because t to the power of 2n, if I let the t squared to be x, it will be just x to the power of n. That's going to be x to the power of just n minus 1. Then I have a degree n polynomial. That is great. That is great. And not only that, I want you to realize when we are working with the polynomial, we work with the solution of it. I want to find the roots of it. So I have some interesting polynomial that is now expressible in terms of a sign, and maybe I'm trying to find the zero of it, right? I want to find the zero of this. Oh, okay, that's great. And you know that x is now in terms of t, where t was the cotangent, so the x here is gonna be cotangent squared theta, right? So that's great. And I want to find the value theta, for example, that will make this polynomial to be 0. And instead of working with the left-hand side, the right-hand side actually gives a clear picture. Because I got what is it, my friend? The trigonometric function, especially the rational form. I'm only interested in finding the solution for the numerator, yes? And I want you to always remember, when does a sign become 0? It's 0 for the integer pi. I really want you to know, okay? I really want you to know. And what's another thing that I want you to know? What about cosine x being 0, my friend? It should be in your head already that, you know, x is going to be pi over 2 plus integer pi, right? That is a great. Okay, so that's interesting. So then let's try to find it. So my solution here, that is the thing. So now I'm going to let that input to make the numerator 0 to be the integer pi. So let's do that. So let's try to use this to be an integer pi. Okay, so for this to be 0, on that right-hand side, I want to make it 0. And for the sine function, then you know that it has to be integer pi. And I'm going to let from, let's say, from 1 to n. Let me make the, the integer as r, where r is going to be listed from 1 to n. Comma. And then that's actually quite nice. Why? Because now I have how many solutions? How many solutions? I have exactly n many solutions here. And then if you have exactly n many, for the n degree polynomial, says who? By the fundamental theorem of algebra, I have n distinct roots. And in fact, this should be all of it, right? According to the fundamental theorem of algebra. Okay, that's great. So let's plug it in. My x here was the t squared, where t was substituted by the cotangent theta. And we found the solution of a theta, which was r pi over 2n plus 1, where r goes from 1 to n. That makes it n many distinct roots. So this has the n many distinct roots. Okay, that's great. Oh, hold on a sec. This is relatively fast. Let's have catch up. Let's have recap. I gave you a very interesting identity of a cotangent plus I to the power of 2n plus 1 minus cotangent to the power of 2n plus 1 over 2i. And that form is very similar to what? The November 2014, wasn't it? So we managed to actually simplify using the DMT, using the cosine over sine, right? After converting the cotangent into something over sine and cosine so that we can use the DMT. And then in the May 2014, you also saw what? That it's very often they try to mix the DMT with the binomial expansion. So we expanded binomially, and it was rather, quite advanced expansion. But we managed to see that it was an alternating for the other one. So if we find a difference, all the even terms are going to cancel out. So we were just left with the odd terms. But instead of working with the t to the power of 2 n, we prefer working with the x because that's the most familiar, the polynomial form we have, isn't it? So we then found the polynomial of degree n with a certain coefficient described in the binomial coefficient. Oh, so fancy right now. And now I even use the trigonometric understanding to find the n many distinct roots using the fundamental theorem of algebra. Good stuff, good stuff. So now for this polynomial, you have how many roots, my friend? You have, if I let alpha 1 to be one of them, you have n many distinct roots. And does it ring a bell from your extensive study with the polynomial? Does this imply anything with the polynomial? Very good. This actually tells me the Vieta's formula. Remember, the sum of roots will be the negative an minus 1 over an. The sum of the product of two roots are going to be just going on and on and on. And then the product of roots will then be the alternating term, isn't it? Negative 1 to the power of n times the constant term over the leading coefficient. That's the Vieta's formula, right? It's very, very popular for the polynomial study. Do you agree? Okay, so yeah, then I can use the Vieta's formula. So these are the distinct roots that we already have. I'm very happy with it. And the Vieta's formula suggests that the sum of the distinct roots are going to be the ratio between the second leading coefficient and the leading coefficient. So that is great. And we already have the binomial coefficient to do so. So let's use it. So it's going to be 2n plus 1 choose 3 over 2n plus 1 choose 1. And yeah, you can just use the binomial coefficient, right? So the 2n plus 1, my friend, choose 3. It's going to reduce 3 many times. So 2n plus 1, 2n minus 1 over 3 factorial. And I hope this expansion is very trivial for you, okay? For the numerator, sorry. And then, yeah, obviously you're going to n choose 1 is simply n, so the denominator will be simply 2n plus 1. So if you do the cancellation with the 3 factorial being 6, you have the right-hand side. So that's good. That's very neat. Okay, so I hope you realize, we're using all the things that we have learned already. The polynomial, trigonometry, combinatorics, with the coefficient and all that. And then the complex numbers. So this really summarizes everything you have done in topic 1. This question alone really visits everywhere that you have done for topic 1 and topic 2. So this is a beautiful, beautiful question. So, let me make it fancy. We knew that the x was substitution for the cotangent squared theta, where we defined theta to be the distinct arguments, right? Then I'm using it, my friend. So this is beautiful, this is great. So obviously, I'm letting r to be 1 to n, so those are the distinct roots. I'm very happy. So then, yeah, I don't want to use the series all the time with the plus, plus. I don't want that. So I use the sigma notation here. That is great. Okay. Okay. So now what? Okay. Somewhat we were given some special identity. We used the DMT and Binomial Expansion, equate them, and induce this beautiful, beautiful result of the sum of the trigonometric value to be the following binomial coefficient. So what? Sure. And yes, now before we move on, I want to revisit May 2011. In May 2011, what you had to prove was one of the most important inequality in trigonometry and calculus. So they gave you this picture. So, I want you to, I implore you to use this, to solve this problem. This is the single most important inequality in your high school diploma. So please make sure you learn them and you know that inequality by heart, okay? Yeah, this is gonna be the comparison between the, smaller triangle, sector and radian, and then the right angle triangle with the point of a tangency, but I'm not gonna go over. But I want you to, I want to show you, I want to remind you, so these questions are asked on purpose because those are the the ancestors' work. Those are the great achievement of the ancestors in mathematics, and that's why we're trying to learn what they have done for us already. We are going to go back to our trace. So in May 2011, we saw this beautiful, beautiful inequality. And with the result that we have derived in the previous slide, I'm going to combine this, okay? So this is also it's going to be the second exercise. I pretty much wrote out all the formula here, but the first exercise to see whether you can derive the sigma index manipulation, right, with the all terms. And then the second thing I'm going to do, this is a second exercise. This is going to be a great practice for the trigonometry, okay? Trigonometric revision. I want you to please try that you're able to show this inequality. So this is going to be exercise 2. This is going to involve some of the trigonometric identity, can be double angle formula, compound angle formula, or Pythagorean identity. So have a look. I really encourage you to do it. It's not that bad. It's definitely examinable. And then, okay, with this inequality, I'm going to use the result that we have done. So this inequality is not free. We got it from the result from 2011 exam paper. But using some trick identity, we can induce that. And then from here, what I'm going to do is to take the summation notation on on the inequalities. If I take the sigma here, so that's great. So I'm going to put a bracket here just to avoid confusion, okay? Then I'm going to let theta to be the r pi over 2n plus 1, which then says this on the left-hand side, exactly the one that we did. This is the sum of roots. This is the sum of the roots of the polynomial that we did, okay? So we already have done that, you see, with this fancy complex identity. So then, so where I'm letting the r to be the, theta to be the r pi over 2n plus 1. So in the middle, it was 1 over theta squared. So I'm plug it in with the reciprocal, then I can have that. But remember, in my sigma notation, in my series, r is the index. Anything else can come out. So I'm going to only leave the r alone, but 2n plus 1 over pi square can just go outside of sigma to make the computation more simpler. So computation is simpler, right? I don't want to keep it there. It's just a constant coefficient. I can just take him outside, which I did. All right, so then I'm just left with this sum of r square. Can you smell? The rock is cooking. Okay, so let's go. All right, so that is great. So then the initial inequality we had was this, but we saw that the left-hand side is the sum of the roots of the polynomial that we found, and this one, remember, sigma, AK plus BK has linearity, so AK, sigma BK, that's the first property that I can suggest using it. And the second property is that if it's just a constant, independent of the K, it's going to be NC, isn't it? So because I'm adding the n many constants, so that's just the C times n. And where 1 is a constant with the n many terms, that's just going to convert into n. Okay, is what I'm saying. So, okay. So then, we already made a substitution with the the theta with the r pi over 2n plus 1 reciprocated square. So that's what we already have done. And on the right-hand side, that's then obvious that the 1 with the sum will change to n if you're adding from 1 to n many term. And that is beautiful. And what I'm going to do is to isolate this by multiplying the reciprocal of the coefficient on all the signs, and they are perfect squares, so they're not going to change the direction of inequality. So that's great. So let's do this. I've done it for you. Okay? And this is now the inequality that I have to write from my extensive knowledge of the trigonometry and the complex number and then the binomial expansion. That is beautiful. That is great. Okay, let's go. So then, yes, what I like to do is now I want to let n to infinity. I'm going to send the limit n to infinity. I'm going to talk about the sum of that series. Okay, so then you need to think about the limit of the left and right. So yes, it's going to involve the squeeze theorem, my friend. Let's see. If you look at the left-hand side, imagine that I'm sending n to infinity. Then it's going to be the polynomial of a polynomial, isn't it? And I want you to remember, if it's polynomial of a polynomial, what you often want to do is to just have a look at the leading term, right? So for example, if you had to work with the limit, x goes to infinity, x plus 1 over 2x minus 1, this is a rational function, but it's very similar, even though this is a sequence where the n is integer and behavior is very similar. But for this one, what have you done? We just looked into the leading term and then divided by the highest degree of the polynomial, which then is going to be just simply x, isn't it? Then if I did, then this becomes limit x goes to infinity, 1 plus 1 over x, 2 minus 1 over x. And if you send x to infinity, you know that it goes to 0. So then the horizontal asymptote here is going to be simply half. So that is great. That's what we did, isn't it? So that's exactly what I'm going to do here. On the numerator, I got a quadratic term, isn't it? The pi squared is just a constant coefficient. You can leave it alone. But on the leading term of the numerator, that's going to be 2n squared. You see? On the denominator, that's 2n squared, perfect square, so that's going to be 4n squared. Multiply by 3. So the leading term, the denominator, my friend, in fact, is going to be 12n squared. You see? Plus whatever. And top and bottom, like this, what are you going to do? I'm going to divide by the n squared because that's the leading term, isn't it? Then the rest is going to be just 1 over multiple of n, where it's going to converge to 0 if I send n to infinity, because it's 1 over n, right? Goes to 0 as n goes to infinity. So that's not bad. So in fact, I'm going to be just left alone with the coefficient 2 over 12. That's 1 over 6. But don't forget that I had a constant coefficient pi squared there. So the limit on the left side is going to be pi squared over 6. Okay? And likewise, if you look at here, okay, so denominator is going to be 2n squared, 2n perfect squared, multiplied by 3, that's 12n squared, plus whatever, I don't care, to be honest. But on the numerator, what am I going to have? It's going to be 2n squared pi plus whatever. And if you want to find the limit of this sequence as well, it may not be the exact same, but and the behavior, in fact, if you divide by the n squared top and bottom, you realize it actually converges to pi squared over 6. Okay? The left limit of the sequence, the limit of the left part of the inequality converges to pi squared over 6. The upper bound also converges to pi squared over 6. But hold on a sec. So left and right, the lower bound, upper bound, squeezes to converge to the same limit. So whatever in between must converge to pi squared over 6 by the sandwich theorem. Okay, but it's quite old, isn't it? So let's call it subway theorem. I want to get some Italian BMT after having learned some great manner from 1960s, okay? Subway theorem. Okay. Yes, so that is a beautiful, beautiful problem of the Basel problem that you often have seen from outside. Oh, there are so many proofs. There's a geometric proof of this theorem in the YouTube, right? The 3 brown, 1 blue. So please check it out if you're keen on working with this type of a Basel problem, which can be extended into, of course, working with the zeta function if you're interested in writing for the math in EE extended essay. But yes, this question is definitely examinable for paper 3 with a lot of hints, you see. If they ask you to prove this using that identity without asking you to use the DMT, without asking you to use the DMT, that would be very, very difficult. That would be very challenging. But for paper 3, it is very likely to ask you to use these hints, use this deductive reasoning to solve it. Okay? So yeah, this, I think, question alone captures everything you have done for topic 1 and topic 2. That's why I wanted to talk about it for today. Okay, so that is a beautiful, beautiful legendary question. All right, so that's pretty much it for me today. Let's continue working with this, past exam paper, and then see why they were asked. Those questions were asked to pay the respect, pay the admiration of the work by the ancestors in mathematics. You see, so obviously they can be put together to generate even greater, and that's what you're hoping to see in paper 3. Okay, good. That's pretty much it for me today. I will see you next time.